want to introduce Mark. Dr. Mark Walters is a professor of teaching in mechanical and aerospace engineering at University of California, Irvine. He's been a member of the faculty there since 2015 and teaches courses in solid mechanics, machine design, and systems engineering. He recently led the effort to revise the capstone senior design courses and is often found helping student projects in general to get the resources they need to engage in meaningful design, build, test activities. Over the last year, he was the UCI faculty advisor for a student design, build, compete project that partnered with instructors and students at Orange Coast Community College. This project earned second place overall at the Orange County Sustainability Decathlon. And prior to UCI, he was a professor at Ohio State University, where he also served as a faculty advisor to the Solar Decathlon team. He was a Fulbright Scholar in Germany from 1995 to 1996, and he received his PhD in applied mechanics from Caltech in 1995 and his BS in mechanical engineering from Brown University in 1990. So welcome, Mark, and I'll turn it over to you.
Great. Thank you, Mike. Thanks for the invitation, of course. And let me make sure. Oh, I'm
going to make you co-host. There you go. I just made you co-host, so you should be able to.
Okay, good. All right.
Now.
There we go.
Yep.
All right. So I will share my whole screen here. Okay. Everybody seeing this, I think?
Yep.
Great. Okay. All right. Yes. So thank you for that introduction. And some of you might be asking, how in the world is this person qualified to talk about systems engineering? And I think Mike, well, he laid it out there pretty well, is that I'm maybe not qualified and I'm looking for help. The other aspect of this is that I think I've bugged Mike too many times, like, well, what about this? Or what about that? And so he probably thought that, okay, maybe it's best if I just enlist the entire help of the chapter. So, all right, so let me go full screen. Get this guy minimized. Good. All right, so I'm not showing my own talking head here, but hopefully that's okay. This is a little sign I have on my door, and I always talk to my students this way, that engineers create the world we want. So it's been motivating. And I'm actually going to go over some background just a little bit for fun. I grew up on Long Island, so I'm an East Coast person, and yeah, I miss the water. This was my early days were lawnmowers and chainsaws, and then outboard marine engines, and then I built this boat here. Probably, I'm not sure how close you are to the water. It looks similar though, just a little bay off of Long Island. So then I did my undergraduate, still playing with engines, and then I started looking at material failure. And I went to Caltech. The master's there is just a very hard sequence of courses, no thesis, nothing. But I kind of got a bug in one of those classes on research seemed fun. So I did a degree, a PhD in applied mechanics on ceramic matrix composites. This was in the aero department. You can see I'm kind of floating around here. And then I did go to Germany for a year, working in the material science department there, working with thermal barrier coatings, sol gel coatings. And from there, I went to my first faculty position, which is at Ohio State. And just showing you what happened there, several different departments again. And I think, maybe the context of this is I've just been exposed to a lot of different things in engineering. Which is kind of interesting to me. At Ohio State, my brother accused me of just being a scientist. So it goes back to that little thing that I had on the front page there. Scientists investigate the world we have, but I was offended by that comment because I want to be an engineer. I want to be creating the world we want. So at Ohio State, then I bugged the dean enough about energy efficiency and the importance of that, and he put me on this student project called Solar Decathlon. And I did 2 of those there, and then I started to teach mechanical design laboratory. So this was kind of the first, what I'd say, real exposure to design and engineering design. This right here is what we called the hybrid air-water conditioning system. We had a version of this in one of the solar decathlon houses, and then we went out and we tried to get this patented. It was a heat pump, hot water heater that also did air conditioning, used waste heat to heat the water, also ran through a heat recovery ventilator, so you could do ventilation as well. So we didn't go all the way to patent, but it was definitely my first real experience with really designing a system. And then I started also play around with students model predictive control for HVAC systems. So definitely departing from the kind of material science side, materials failure side, and went overseas and worked for a year on a sabbatical as at an institute for building physics. So doing energy modeling there. Actually left directly from Ohio State after that sabbatical and came here to Irvine, and was the first professor of teaching in the School of Engineering. So I've kind of left that research world that most faculty live in, and have been focused on curriculum. So I have a poll here, which I know you're all at computers. So I'm now interested in a little bit more about you, just so I know my audience. Are you a student, a faculty? Where are you in industry, retired, or another? If you go to this website here, pollev.com/MarkWalter169, then you can fill out that or answer that poll. It should let you in, or you can text me or text pollev. And you just need to send MarkWalter169 to this 22333. And it'll pull up the poll and you can just answer it there. So this is one of the things that we do as professors of teaching. We're very concerned about pedagogy and just improving the way we teach, and one of those things is active learning. So I was grateful to Mike for suggesting that we make this a much more active session here with just some dialogue or kind of a workshop session towards the end. So this is also something we do in active learning, is more polls. Okay, but it looks like people are having trouble, because usually I see an update here. Is this working?
It's asking me to log in.
I am having to make an account on here. I'm really close.
Or paste a direct link. Can you paste it in the chat, a link?
So what I was going to do is go ahead. I had shifted over to the
okay.
texting.
But let me see here, because I think this is a mistake on my part. I should not have. Let me see.
Oh, it says pre-register required.
Yes, and I'm going to turn that off right now. Okay.
Let me try it again then.
Yes, so it should work now. So my mistake. I should have made it not registration. So let me fix this one as well. Usually when we do this in our classes, I want it to be restricted to only people registered for the class, and I didn't realize that would default on here. Okay. All right, by any chance, is it working now?
Yep, I'm in.
Great, okay. All right, good that I managed to find that problem.
It's not our first one. The first one's. Oh, okay.
Yes, wrong one. Sorry. There we go. Good. Okay. All right. I'll continue on here. and I'll maybe come back to this afterwards and look at the audience. You, I think, all know each other, so this was more for my benefit. Good. So there will be one more, which is a more important poll later on before we go into our breakout rooms. Okay, so a little bit about my work here at UC Irvine. And as a professor of teaching, I'm actually what we call ladder rank. So I have tenure. I came with tenure because I had been at Ohio State for about 17 years. But as a tenure rank person, we still do the three things, which is teaching, service, and research or creative work. But the balance is different. As a professor of teaching, it's supposed to be more of an emphasis on teaching. And I like to say that I do about 20% of this creative work and then 100% service and 50% teaching. So I think that characterizes my hours per week pretty well. And the service is pretty heavy, largely because I'm involved in the student projects, and it doesn't always fit into teaching. Mike kind of alluded to that, helping students get the resources they need. So these are some of the things that I've been involved in what I would call service. And in teaching, I've taught a variety of courses here, a large variety. But I think more relevant here is I've been teaching mechanical engineering design and a couple sections of what I call model-based engineering. So that's what we're going to talk about is about these courses. But the context for these courses is it's in the context of projects in general and project-based learning and what we call capstone design projects. So let me first go through our curriculum. It's a pretty typical mechanical engineering curriculum. And you can see very, very heavy in the math and physics in the first 2 years. So this represents a first year. So this would be freshman year. We're on quarter system, so we have 10-week quarters. If you were to start in the fall of 2022, these are the courses you'd take. The 7A and B they're optional courses, but they're kind of an introduction to engineering. It's a fairly popular course now to do this for freshmen, because the physics and the math and the chemistry is so draining that you lose sight of why you want to be an engineer. So in our 7A and 7B, these are they have been quadcopter courses. So students build quadcopters, and they fly them. They do 3D printing. So it's very hands-on, and just meant to be a lot of fun and expose students to different aspects of engineering within that quadcopter platform. So very different from when I went to school. You start to get into some of the engineering courses in your sophomore year with statics, and you've got dynamics, thermo, fluids, first fluids course, a materials course, and a circuits course. And going into junior year then, something I should also mention is we have about 40% transfer students. About half of our students, I have half here of our graduating class, consists of transfer students, and they enter in their junior year. And that makes this fairly challenging. We can't just add courses in the freshman, sophomore year because these transfer students wouldn't get those courses. So we have to be a little careful about that. Okay, but this is now more of what you expect from mechanical engineering degree, more thermo, more fluids, dynamic systems, heat transfer, thermal science. There's a CAD course in the middle of your junior year. It's the strength of materials course, more materials, controls, so fairly typical. Any questions about the curriculum before I continue on?
Could you go back? Oh, I just wanted those yellow boxes it was in
Yeah.
Green. They're green. Engineer and A and B, 7A. Yes. What were those again?
They're we call them freshman engineering courses.
Okay.
They're open to everybody in all of engineering, so chemies, BME, everybody, and they're meant to kind of excite or keep the excitement about being an engineer.
Gotcha. So they're just sort of overview flavors of what engineering is. Okay.
Yeah, and it's done. It's not like a seminar where they talk about different types of engineering. They actually they take a quadcopter platform.
Okay.
They will build the quadcopter. They do a little bit of CAD there. They talk about materials. They do the electronics. It's a lot of very spoon fed. I mean, these are freshmen,
Uh-huh.
but it's hands on.
So that work there with the quadcopter that covers a lot of the various potential disciplines that they'll later be
Yes.
exposed to. Yeah.
Yes, absolutely. They do have some different options there, like so it's not as relevant for a BME student, but they might have some other BME projects that are part of this as well.
Okay, thank you.
I mentioned that kind of in passing. I said, oh, it's mostly spoon fed because they're freshmen. But it's pretty amazing what freshmen can come in with, what they do in high school now.
Oh, yes. I do STEM fairs, and I am amazed at what these middle school and high school kids can do. Literally, like there's some that when we were there as a team judging them, there were, I said to the discuss with my judging team members, like these guys should patent this, literally,
Right.
or productize it at least,
Yes.
So
yeah,
I'm sorry, I thought I heard somebody else who had a question.
Yeah, it was just going to be a little bit about transfers. Does
Yes.
California support any kind of, like, looking at those two courses you just described, is there like a junior college way to get credit for that, or credit for military, or
Great question. Yeah, so we do have a relationship with two local community colleges, and they have a transfer. We have a transfer kind of program with them, and they actually do offer these two courses. But most of our other transfers from other schools do not have access to these two courses. They're not required, so it's not a required part of our curriculum. I don't know the numbers taking it right now, but it's probably about 75% of the students who join as freshmen, they will take these two courses.
Yeah, it sounds super fun.
Yeah.
I'm a high school senior, so yeah, okay.
Yes, good. Yeah, a lot of schools have this now. I mean, when I was at Ohio State, even when I started there in 95 or 96, we did exactly that. We developed a freshman engineering sequence, and the sole purpose, well, I shouldn't really say sole purpose, but the main purpose was retention. Mm-hmm. Back in the mid to late 90s, the concern in engineering was retention, that mm-hmm. so many students were dropping out because they had to take this math and physics, and they couldn't see the light at the end of the tunnel. So that was the purpose of those freshman courses, and a lot of schools will do this now. Good. So the transition here is into these design courses. So this is the old curriculum actually. As of this quarter, so about 7 weeks ago, this is a little bit different now, and I'll be talking about that. But this is the Mechanical Engineering Design course 151, and then this 189 here is intended to be the capstone design. And when I came, this is what it was like, and it was quite problematic. So, and it was problematic in the 189 classes. So there were about 20 to 30 student projects. They were student-led. There was an advisor somewhere usually, but it would be the students who actually let other students onto their team. And the students would decide what to build and do all the timing. And it was great experience for those few students who were leading this. And frankly, they were putting a tremendous amount of time. But it was a great experience for them. Not such a great experience for everybody else. And some of the teams were, particularly the race car teams, the Formula SAE, Electric, and Baja. Everybody wanted to be on those teams because everybody wanted to build a car, and we have a strong car culture here in Southern California, and so it was definitely problematic that the students were leading this. These were some of the other projects that were going on. I'm leaving a lot out. This link here will document most of them. So some of the problems: freshman to senior, there were no prerequisites for this, even though it's supposed to be a capstone design. It should be something that you take after you've done all these other fundamentals, and you can use those fundamentals in designing whatever it is that's being built. But anybody would join. And a lot of the students who are on that getting graduation credit for 189, degree credit, well, some of them were not doing anything because the teams were 30, 40 people. Others were just there to weld some tabs, so not really doing any engineering analysis. Students would join multiple projects, so the commitment was very mixed. No little oversight. Sometimes it was just a social club. Even drinking going on in the labs and things like that. So very problematic. No documentation at all was required. And so a lot of the advisors, what were they going to do? They'd just give everybody an A. And so I characterize this with just being a crafting effort with very little technical engineering. So our first attempt to change this was just telling students you can only do one of these projects per quarter. It's only for seniors, and we would have weekly check-ins. And in the check-ins, we would be asking them, what were your requirements that for what you did this week? What requirement were you trying to meet? So document that, do more planning, do more engineering. And we had other students in these check-ins, so there could be some dialogue. And then there was a quarterly report as well. So that was our first attempt, and not a lot of support from the advisors. So it wasn't perfect. And then the other part of the problem are just the numbers. So this shows where we were in 2009. We had about 150 in these projects. They would take these projects, this class, over and over. So the graduating class here was probably closer to about 150. But they would take the class over and over because it was also an easy A. So this was the enrollments, and then enrollments in engineering just started to go through the roof. And so we'd have 396 students in this quarter here. This was the peak that we reached in 2019 in this kind of project classes. This is the point where we introduced the check-ins, and students like, oh, I don't want to do a check-in. I don't want somebody to ask me why I'm doing this work. And so the students started to take was 93. And it was just a place for them to work on the project. Again, little or no assessment, but there was no degree credit for that course. And so we didn't care. I mean, as faculty, we weren't as concerned about what the learning outcomes were. All right, so I'm going to transition a little bit to just talk about teaching the 151 course. I started teaching that in the spring of 2018. And this was a 1 quarter required course that would teach the engineering design process. And it would have a common project then. So everybody would do the same project. And I'll show you some examples of those shortly. Problematic, if you look at this curriculum again here, this 151 was offered in the winter, but students would be taking 189. They might be taking it as a freshman, but they would taking this, well, the 189, the capstone design, well before they learned anything about the design process. And so again, part of the problem was the timing of this and the requirements for it. But the course itself probably similar to what some of you have seen. This is a pictorial view of it. Define the problem, do a preliminary design, concept generation, selection. Of course, in the problem definition, you're going to identify the needs and the requirements. And then you move into detailed design, and there's iteration there with prototyping, testing, redesign, verification, and so forth. And then you end up with a final design, do some validation. These were the lecture topics that we had. So 3 lectures a week for 10 weeks. And it included other things like ethics and inclusivity and things like that as well. So one other problem that we have here is our other course on kind of mechanisms wasn't teaching everything. So students in mechanical engineering didn't have machine elements like fasteners and gears and bearings and lubrication. So I was adding that into this course as well. So it became pretty packed. Good, I'm gonna go through and just show you one of the common projects here. This one is a golf ball launcher. You can see some of the student work. It's not completely open-ended. They have a very defined task that they need to do, but as you can see, the designs are very, very different. The majority of these would be a spring-loaded, this one shows nicely here, a spring-loaded design that would, in this case, they were punching the ball through. We would add a number of requirements to this, like that they had to have an automated angle adjustment system that would tell you what the angle was. They had to have a velocity measurement system on here as well. And so we could have them tell us their velocity measurement and their angle measurement, and then how far the ball went, and we'd know pretty well whether their sensor system was working. I'd say we'd have about maybe a 30% success rate. And success rate would mean, to me, just getting close to getting the ball into a bucket, and the bucket was somewhere between 5 and 10 feet away. We wouldn't tell them ahead of time where the bucket was. Well, we would tell them when they came and set up, but they had to have in their angle adjustment code, they had to have some calculation that would tell them what angle to go to in order to hit that distance. So probably getting in the bucket was maybe 10% success. We would occasionally see the spinning wheel attempt to fire a golf ball. This never had any chance of success. It was really only a spring system that might work. Anything strike you about these designs?
All I can say is it does remind me of a lot of the typical designs I've seen in high school efforts as well. You know, they're very rough prototypes. Obviously, they're limited. Their biggest limitation, the greatest thing about these young students is that their only constraint is money. It's like, and then creativity seems they have no bounds, you know?
Yeah.
So.
The only thing I say is that I don't know if this is done by a Raspberry Pi type of computer.
These are all Arduinos.
Okay.
Yeah. Yeah, we would. They would have usually enough budget to make what they needed. You're right about the creativity, and you would always see very different things here. I mean, one of my problems generally with the creativity was that it wasn't always vetted. And that was what we were trying to get across here, is that you really need to do the engineering analysis and check your requirements to see it would work.
So that's a good question. So are you saying that they were mostly not doing engineering so much as, crafting or artistic project?
Yes, I would absolutely say that. And I mean, part of the issue there is just that I think bigger constraint or limitation was time. So they just didn't have the time necessarily to do everything with more analysis and more engineering. So they would end up making something, and then that's what they would do. They would go ahead with that.
Yep.
And so you end up with the tape and the things that make it look more like a high school project. So yeah, so this was one project. Another one here was a lift. So they had to, in this case, was a water bottle. They had to lift it from a starting point. So we would define, this would set the requirements, at least the geometric or functional requirements. They had to lift the bottle up and then slide it onto the platform. So these were a couple examples of what they would build there. Obviously, a lot of 3D printing. I love their pillow block bearings here that could probably work on my car. So a lot of over design going on as well. I would typically have a weight measurement as well. So we would have a feel for whether they were over engineering based on just how big they made stuff. Yeah, this was a very interesting design here. It actually was a boom that would rotate, and they had a very unique mechanism here for grabbing the top of the bottle, and it worked flawlessly. So sometimes you'd find something really out of the box that would work well. One more example here was a water hauler with a heated cabin, and they had to do a course that had a ramp and had a bunch of bumps on it. So these are some examples here. So they would all receive one of these RC cars. They also had to automatically couple the trailer. So they weren't allowed to touch the two. They had to back the vehicle into some kind of a mechanism so that it would couple automatically, and then drive off and do their course. And then we also, during that time, they had to keep the cabin heated, and we would measure the temperature there as well. So we definitely pushed them. Okay, so I think one of the points I want to make with this, and this came out when Mike visited, when I first met Mike, it was a couple of years ago, maybe 3 years ago now, right?
Yep, that's right.
Yeah. He was listening to these projects that we were doing, and he's like, these are systems level projects. And, I felt like I had to do that because we would have 6-person teams, and I didn't want anybody just sitting around on this team. I wanted each person to take responsibility for something. And we wanted to make, like on this project here, we added the heat transfer. So we added, and we always had electronics as part of it as well. And all this had to be integrated. So, and we were at an emphasis on requirements, concept generation, selection, analysis, verification. We had all these different machine elements that were in almost all the projects. This should say, given the nature of the projects, most of these would fit well in a V diagram, right? With integrating different subsystems, just doing your detailed design, and then going up the other side. The most recent versions of this class that I had run, I also would ask for a black box and a gray box, or the functional architecture for this. So I came to realize that I was already doing a fair bit of systems engineering. Okay. So I'm going to go on here with a few more slides. I'll probably pick up the pace because it's mostly just letting you know what we've been doing. I do still want your feedback on curriculum and what you think is important. Starting this year, we took a new approach. We got rid of the 189 completely because of the accountability and the widely varying experience. And then 151, it was just kind of too short and not really open-ended. So replace this with a 2-course sequence, and there's an open-ended project that goes for the 2 quarters. Each project is now different, or can be different, and there's a sponsor, could be from industry. teams are still about 3 to 6 students, and they're forced into a lab section, and they meet with instructors during that lab section. And I think more importantly these days, they are able to work in person because there's a fixed time where we know they're all available. If you try to get 5 or 6 students together now, just random students, it's almost impossible. Between courses and work and other family responsibilities, it's almost impossible to get them all together. So we had to get them into the registrar, into the course enrollment system, so that we knew that they were all able to work together. We've added that they need to use the MATLAB requirements editor, and they're using System Composer from MathWorks to develop a functional architecture. They do a project definition presentation, preliminary design presentation, concept mock-up presentation. That's all in the first quarter. The second quarter is an emphasis on critical design review, a CDR, with then a couple prototypes and final design. So this is the new course that we just started 7 weeks ago. I don't think I'll go through this in any significant detail. The lecture topics are very similar to 151, especially in the first quarter. But you'll also see a little bit more STNR, black box, system architectures. So adding a little bit more language of systems engineering. So this is the first course, 151A. By the way, those other projects like FSE, race car, and so forth, they can do a component of that project in this course. So say the suspension system, they could bring that in and over two quarters design that system within the framework of this course, and hopefully end up with a better suspension system than if they had just kind of crafted something on their own. But those student-led projects are now like club projects or extracurricular projects. Our 151B, kind of mentioned it already. They do some redefinition and updated milestones, then a CDR, and then a couple prototypes. So that's the plan for 151B. We haven't run that one yet. Okay, so before I go into my model-based systems engineering, digital twin, I have another poll here. This should be live. So I'm curious what you think, based on what you've seen so far, whether you think every undergraduate engineering major, we could just focus on mechanical engineers, but maybe this is true for all engineering majors, that they would have a separate systems engineering course, or maybe what I've outlined within an engineering design course, which pretty much every major does. Every major has some sort of a capstone design course nowadays. Is that sufficient? Or should there be a separate systems engineering course? So I'm curious what you think about that. Good, and so I want to talk a little bit about a new technical elective. So I've run this twice now. This is in part because of conversations with Siemens. Siemens donates software, and I have interactions with them and with a Siemens partner that Mike knows very well, with Ceratec here at UC Irvine. I had that question about engineering design and systems engineering. Is it one and the same? Should it be separate? I think, as you saw, we're integrating different elements. They're interacting elements, they're interfaces in those projects that I did within an engineering design course. And we're controlling the design from concept into prototyping. But then there's more model-based engineering, emphasis on modeling and simulation, SolidWorks or EllerCAD, and then simulation. It's so easy now, and all the students do that. They will, I think students are afraid of pen and paper. If I ask for even the simplest strength of materials calculation, like what is the stress in an axial bar given a simple axial load, they will still put it in CAD and run an FEA simulation on it. So, the simulation is king now. So we might also call this simulation-driven design. And then there's model-based system engineering. And then there's the, what I call the holy grail, the digital twin. So what everybody talks about now. So with this in mind, I developed this technical elective, and I'm going to go back and look at this poll result. So 57% of you are saying yes, it should be a separate systems engineering course. And that's essentially what I started to do there. But I found that I was repeating myself. Everything that I was doing in engineering design in this course, I was also doing in this technical elective. I was using a pre-made theory curriculum from Siemens, and I'll show more of it in a little bit here, but they had a case study system, and they went through all these systems engineering topics here. You're probably familiar with many of these. Some of these were very lengthy lectures. It was also a 15-week, so it was a semester-based course, so I wasn't going to be able to cover all that material. And then in the lab portion of it, they use Team Center and they use System Modeling Workbench for architecture, and then some different Siemens tools. So the overview of this was, and the case study part of it was an electric longboard. So again, developed in collaboration with Siemens. There's that branding on there. But this is what they actually built at Indiana University, Purdue University, Indianapolis. And they did it using Team Center, but just kind of showing kind of tutorial wise, all of these were, the lab was all just follow these instructions. But they did system design, the 1D modeling with MSIM, then used demonstrated NX, your simulation with SimCenter, and then also used HEADS for project optimization. These things here I did not play with, but Team Center has the manufacturing side built in as well. So almost done here. I have taught this course twice, and I'm still not very happy with it. I'm still trying to find the right formula for it. The first offering was an emphasis on the Longbird curriculum. I used Team Center at that time. I had a working server for it. Followed most of what they were showing in the curriculum, and we did all these different examples. I did show a little bit of MathWorks, System Composer, Simscape, and Simulink as well. And then we required NX certification, just because certifications are valuable. So it was essentially the first attempt there. I think there was a bit of a heavier emphasis on the system modeling workbench. In the second attempt, which was last spring, I did the same systems engineering theory from that curriculum. I cut a little bit out because, again, some of it was repetitive, but also just going through SysML. I might be making you haters if I say this, but or hate me, but I couldn't see the students really benefiting a lot from learning SysML language or making architectures in all these different languages. But I did emphasize architecture with Capella, and Capella has this very nice tutorial. So I made the students follow that and submit screenshots. We still use some of the demos, so the 1D modeling, the NX, SimCenter, but usually these were just short assignments where they just followed the tutorial. We did do more with MathWorks and Simscape and Simulink because I'm always worried about teaching too much of a specific tool. And then in the bottom here, certification in something was required. But I think another interesting thing was really trying to push to a 1D model of an inexpensive race car, or RC car, I should say. So this was the assignment. They had to develop this model. They did it within AMASIM because they already had a lot of the components there from a different example. But they had to add a battery to it. So running the DC motor, characteristics of the load. How do you turn that translational, rotational motor into wheels on the ground, moving a mass? So this is all a 1D model, and it'll output then displacement, velocity, and so forth. So they had to actually take apart the car. They got two cars and teams, and they took one apart and characterized the different parts of it so that they could put in parameters for these different model elements. And then they had to run 3 runs on a flat surface, 3 runs on a sloped surface. The slope can be adjusted within the model here. And then different state of charge for the batteries, and try to then and then make measurements of these velocities for the actual second car, and try to model that in AMASIM. So that was the big project from my second offering. All right, 2 slides. There's still a lot of missing modern tools in a modern curriculum here. Engineering is much more automated than it used to be. There's access to information with very good answers, AI included, access to simulation, which I already alluded to. There's some universals here: developing intuition, insisting on the critical thinking and a growth mindset, more of an emphasis on learning as opposed to just getting through. I'm just here to get that piece of paper versus I'm here to learn. And then encouraging grit and resilience, I think, is important these days. And so it's very hard to change the mindset of faculty. I'm still trying to figure out how to do this, how to change a curriculum. A little while ago, we thought that we might change from quarters to semesters. That would have been an opportunity to completely revamp the curriculum. But without such a big change, it's very, very hard to change your courses. There are faculty here who will not give up what they teach. They will say it's the most important subject in all of engineering. You know, steam tables, right? Most important topic. So, so it's very hard to do that. We can't add units unless we were actually to acknowledge that this is a 5-year degree. But at the same time, we need to add something. If we add something, what can be cut? Furthermore, employers are looking for skills, but university teach fundamentals. So students have way too much going on. They're too distracted. They focus on the path of least necessity, of least resistance, just out of necessity. I do project-based classes, but I also don't think that everybody should do project-based classes. Everybody wants to do project-based classes. Students want project-based classes. I think they want them because they know it's so hard to grade. It's so hard to assess what they're doing because these project-based classes are open-ended. But I do think we need to introduce simulation much earlier. So, went very long.
So Mark, I think what you'll have to do, given the time, is pick one of these, and we'll just get general feedback from the group on one of these topics.
Yes, I think it's probably right. So I'm sorry to go too long. I hope it was interesting. I had originally intended to. Well, I had this Google Doc here, and I was going to have the breakout rooms fill it out. So yeah, I mean, let's just like Mike suggested, let's just open this up. And Mike, rather than pick one of these, I think maybe whoever wants to say something about any one of these would that'd be great. And I'm gonna sit here and finally shut up and take some notes. But Mike, do you want to read through each one?
Well, we're out of time, so I'm gonna assume I'll start, and that'll give everybody time to read the three. So I'll start with the learning outcomes for me around the MBSE class. I would definitely want to make sure the kids learn the basic models that are used in model-based systems engineering, the functional model, parameter, requirement, and behavior. That way, they, and I agree that the outcome shouldn't be that they're experts in SysML. I would teach them just enough of the tool or just enough SysML to make sure they got those four diagrams, the four main diagrams nailed.
Okay, so the four main diagrams with enough of the language.
Yeah, or four main models, I should say.
Yeah. Can I follow up? Do you think that can be done within the mechanical engineering design class, or do you need a separate systems engineering?
So I think what I see is it's great that you have the 151 AB and you have the MBSC as the elective, because I think what will happen is if the kids take both sets, the kids in the 151 52 will be thinking, geez, I wish I had this MBSE class before I took the other class. And I think the kids in the MBSE class, if they come along later and take 151, they'll be glad they took it. And the ones that took 151 51 B, or the ones that, where am I getting myself confused? And like I said, the ones who take it second will be happy to take 151 after the elective. And the ones that take it before the elective will go, oh, now I see how to apply this stuff. So I really don't think you can lose.
Okay, thank you. All right. Do we require everybody to at least say something?
I'll say something next.
Thanks.
The goal here, I guess, I think that I thought you're asking us is like, what's the best way to teach them systems engineering methodologies in, engineering when they engineer projects, right?
Mm-hmm.
So what I was thinking was you showed there the classical systems engineering V of standard processes, which is great. It's a great pedagogic tool. And we all know that's an idealized model, and things don't always flow so linearly with that. But, and maybe you do this, maybe I just didn't catch it, but what I was thinking was if you had a course where you took each of those blocks, process blocks, requirements, elicitation, requirements derivation, design, et cetera, all the way through validation and stuff, and sort of gave lessons, I don't know, a few weeks, or I don't know what the time, how this would actually be scaled out in time, but let's say you do 1 month on one block, another month on another block. And as you're teaching the process, they're on the side, they're executing that process on their overall project of building whatever it is, a car, or a plane, a radio, or whatever.
Yeah, that's sort of what we try to do. We have to really front load the kind of the business analysis portion of it and the problem definition portion of it, because we don't want to spend a month defining the problem when they really only have 4 months to do the whole project.
Right. So that's what I was getting at. It's like any one of those could almost be a course that there's multiple techniques to elicit requirements, for instance, simple as that. But so the other thing I wanted to ask is, you had talked about them going through that in some of these and some of the requirements of the course, and I imagine there were artifacts other than like the delivery of the actual prototype, there were documentation or electronic digital modeling artifacts that were graded artifacts that they were required to accomplish, right?
Yes. Yeah. So I think a lot of that we try to just put into presentations now. So like a problem definition presentation, we'd be grading their requirements that, the stakeholder needs and requirements, and then system requirements out of those presentations.
Okay.
Yeah. Otherwise, it just kind of comes like as a report. There'll be probably a report at the end. Yeah. But I like your.
Well, I guess what I was getting at is if you sort of know, have idealized of, from best practices, what may be some of the, artifacts that they should sort of shoot for them to look like an actual, successful artifact would kind of be towards, and then, help guide them toward it to producing that way or something. Like when they produce the requirements, and then first, like it's kind of high level, there's operational concepts and use cases and scenarios, and then it gets into more functional, and then maybe break that down to systems, and then you've got traceability matrices, or that's the documentation wise, or how do you do that in an MBSE sort of environment? Either way, you could go and sort of instructing them, giving them guidance and how to do that, and then grade that at the end, I guess.
Yes, thanks. That's helpful.
Yeah, my particular background. So I don't know, other people can speak up, but with systems engineers, like in any engineering thing, in school, when you're starting out, they teach you all the various engineers, like your mechanical engineers, probably especially, you learn fluid mechanics, you learn electrical engineering, you learn mechanics, you learn physics, you learn, all the variety of engineerings. But in a practical sense, when you get out, it's usually only after once you become a senior engineer that you're actually dabbling in all those and being, managing all those sort of things. When you first come out, you're like very focused. And sometimes a lot of people are focused in the career the whole way. Like me, for instance, my major focus is on actually requirements and assisting with the program management, assisting with them in assessing overall project risk and stuff, and validating the delivery of the product with customer and stuff like that. I don't do any MBSE or architecting. I really know very little about it, so it's hard, I guess, from that. Like each of those disciplines you could have a whole course in itself, and so just trying to do the whole thing in 4 weeks, I can see that that's difficult.
We have one lecture on project management, right? That should be a whole course,
right? Yeah, well, there's a whole profession, project PMI Institute, actually we've had talks in the past of the sort of the Venn diagram of how does systems engineering management overlap with program management. We've had different people give talks on that. Those are interesting whole concepts, and I can tell you it's done differently, across the board. There's no one like best way to do that sort of stuff.
Right.
Okay, I don't want to really give somebody else opportunity here.
Thank you.
Hey, Mark, first, I wanted to say thank you, but I also want to kind of hit what it would be important to make sure system engineering is not. Because I think we were born out of software. but we're not really that, because sometimes you hear systems engineering and you think that's what that is.
Mm-hmm.
So, and I also put in the chat, I think it's a different thing. It's a meta engineering, and I would hate for too many engineer types to believe, and I was an industrial engineer first training 30 years ago. I would hate for too many engineers to think, yeah, I took that. And like, as Clinton said, if that's not his bailiwick of making the system drawings, knowing that that's an actual science, just like, chemical engineering, I think that's just an important thing to get out to people.
Mm-hmm. Yeah. Yeah. Interesting when you talk about software, it seems like a lot of our so-called tools, they come out of software design, which is a little bit strange, because they don't feel like systems.
Yeah, and I think they're trying to over time morph it to where it's more humanist and less software-ish. But the field is only 20-some years old. So anyway, I admire what you're doing. It's a bold attempt, sir. Thank you for doing that. I hope a lot of freshmen find their way to you.
Oh, thank you. Yeah, it's a big experiment every day, it seems. I found I had to teach a course. It used to be like I teach a course 3 times, then I'm comfortable with it. It's taken me forever to get 151 to where I'm comfortable with it. And now I've changed it to 151A and B. And then the model-based engineering is even worse in terms of figuring out where I really want to take that course. But got to keep giving it, and it'll eventually get somewhere, I think.
Okay, it's Kaz here. I like the fact that you threw up that the V, a standard V model. But while you're going through some of these classes, it might sometimes start out with the V and then have like a circle and say you are here at this point or phase in this, and then keep reminding people where they are along that path. And I don't know how much you emphasize that, because I'm also thinking too, I mean, when we talk with Courtney Wright about getting your ASEP right out of school, that you take the class and if you pass or do reasonably well, it's they have like an equivalency. So I don't know if you've talked to her at all, because if you maybe morph just a little bit or craft one of these classes or both of them into something that has that, again, you can come out of this with an actual certification as well. Which again puts an extra feather in the hat. And again, I think you showed the systems thinking behind putting the systems together. So I think that's
right.
And I have seen we had I don't think we recorded it. We had one of those STEM projects show up, high schoolers, I think they were.
Right.
And they gave a demonstration. It was at APL here nearby, the Johns Hopkins Applied Physics Lab. And they had a new building, I forget what it's called, 100 or something. So they had a big area there. And what they had done is, I guess a couple of the teachers had some like system engineering background or knew a system engineer, and they went through all the little, like project things that they needed to do and to go along and do the validation. But what they developed was a machine that would shoot baskets, basketball into a basket. It would point at the thing, in other words, it would first find the backboard and then determine the distance and then aim and shoot. And apparently, the thing would be very accurate. And I was like, and these were high schoolers. I was like, oh my God, I don't think I could do that now. I mean, it was just flabbergasted to see that happen. But when they went through that whole process, the systems process to do, all these different things. Now, granted, they didn't have, the fancy tools, MBSE tools or something like that to help them. But I was just amazed at what they were able to accomplish. But they did follow, like a system engineering methodology to achieve that. And I think, obviously you can do that because these are, people that are getting engineering degrees, but at the same time showing them, the practical sense behind it all. And I got to admit, when I took some classes, I guess the teachers or professors, what have you, did not maybe drill that into me as much as maybe I needed it, or maybe they just didn't talk about it as much as maybe they should have. So, no, I find this very interesting. Yea, verily, go forth and multiply. This sounds really good.
Thank you. What was the certification that you mentioned?
The ASEP,
ASEP.
the Associate System Engineering Professional out of NCOSE. And I mean, there's levels, but the first level is basically, if you pass this exam, pay your fee, you can be an associate system engineer. And it just means that, yeah, you're a beginner. But at the same time, it's kind of like what they've been doing lately is they've been certifying certain classes that once you take the class, you pass it, you are allowed to become an ASEP. You might have to pay a fee or something to actually get the full certification, but it was kind of interesting. And so Courtney Wright has been working with some universities about that, and that may be something that's worthwhile because you are talking about certification here, as well as the fact that it looks like you are teaching some of the aspects of system engineering. And then again, you might have to tweak or tailor a couple places to get that to happen. And then that might also be another attractiveness and give the class or those two classes a little bit more weight or mass to it, so to speak.
Yeah, Mark, do you know Courtney? Have you heard her?
I do not, no.
Okay.
Yeah. Oh, actually, yeah, I think she probably has I'm certain on the NCOSE master website or on YouTube, she might have like some 10 or 15-minute clips out there. I don't know, only because I'm beyond that, and then we usually have her talk at our gala every year, but this year she's had some medical issues and we don't think we can get her to talk. But meanwhile, it's like there's been a couple of times she's talked about this, the way they're trying to get certain universities around the world involved in some of this, and I think that's very good. Now, I don't know, how familiar are you with all the NCOSE material?
I've seen the Book of Knowledge.
Oh, the CBOC? Yeah.
Yes.
That's an intense book. Anyway, yeah. I don't know if you look up, SEP, which is System Engineering Professional Certification, on the main, NCOSE site.
Dan just put a couple of items, put in a link.
Yes.
Oh, okay, good. All right, good. Chat. Thank you, Dan. All right, good. All right.
Yeah, and Mark,
or David, did I say Dan? Yeah, Dan.
Yeah, Mark, I'm in I'll call it an after hours class for a person who's beyond the age of 60 that Mark teaches. So if that becomes something you want to do, let me know, and between me and Mark we can get you stuff. He's the former communications guy. Now I'm the communications guy in training, as I screw something up every month is pretty much my method. And then folks direct me the right way. But yeah, we could help you consider that. From Paul, it's about an 18-month process, though, to, hey, we're thinking maybe we'd let our students get this certification. It's a program that has the V in it. And it's, it looks at the CBOC kind of thing. So we can help you go down that path. It's not super quick. It's a year and a half kind of thing, but doable. Over.
Right. Yeah, this is very interesting and a good idea. I mentioned that Siemens was here today, and they actually mentioned the NCOSE certification. So I'm glad you also brought it up, Kaz. And the idea of creating a course that would get students to that point is also very interesting. What Siemens has been pushing lately is the Michigan systems engineering curriculum or course that they've set up there. I'm gonna be checking that out. I'm curious how they are with certification as well.
Okay. Any other thoughts for Mark?
I Sorry, are you going to publish a book at some point, Mark, so I can get your book and get a copy of it? I know I got to get Suzette's book.
I just
Now I
ordered
want your book.
I'm definitely a ways off from doing that.
Yep.
I also yeah, I mean, I still need to figure some things out on my own. And there are a lot of, in terms of engineering design, there are a lot of books already out there. Interesting books. I think if I did something, I would make it more of like a short course.
Okay.
Yeah, and I wanted to I've just been reflecting on everything that's been said, and a lot of things, Mike, that you've been talking about. We actually talk about in the book, and what we do is bring a lot of those concepts together in a way that we are helping industry at large take all these best sort of success patterns that we're seeing, and how to, the use of digital twins even, and growth mindset, and so many things that you talked about. But how do we do it in a way that we can be more responsive and reduce handoffs between various functions, which I think in your project-based approach, right, that's one of the things that kind of comes together, right? It pulls the different kind of learnings together in a holistic way. And I think there's a lot of synergies with what you were describing. And one of the things, part of the reason I called in tonight, because my son also just started at Clemson in engineering, and with Robert and I publishing the book recently, and wanting to figure out, like, how do we take these messages of these success patterns that we're seeing for building cyber physical systems into the universities in a way that we can support and help provide sort of a vision forward of what we need to do, based on the foundations of the successes that we've had in the past. But what is that vision for going forward as things, the pace of change and having to deliver capabilities faster, is becoming more and more prominent. So I don't know that helps you at all, but it's been very interesting to listen to the challenges that you're facing, and then how do we pull all this together to build the workforce of the future? And so when they come to our companies, that they are armed, maybe not with all the skills, obviously, that they need, but some skills, but most importantly with that growth mindset, so that they have some foundational skills to get started, but knowing that it's a continuous learning journey, and just getting them into the fold, and how they work together as a team is so important, which you addressed that a couple of times as well.
Yeah, absolutely. Thank you for that, Suzette. I just pulled up the Amazon site for the book, so I won't lose it after the chat closes.
Yeah, we use a CubeSat as an example, because, I don't know, satellite constellations just seem to be of interest these days.
Yeah. But I like what you said about the workforce of the future, and that's a little bit with the conversations with Ceratec and with Siemens, that's kind of what it's about. I mean, we're coming up a little bit short right now the way we do things at the university. So I think that's kind of been my focus here, is thinking about that curriculum. Does it serve, like you said, the employers' right degree?
Right. And I assume I'm going back to the last question on the slide, if I remember it, about how to assess projects. And I do think that's hard for sure. And I'm sure you already use some sort of rubric, because I've taught a little bit at the university as an adjunct faculty. And that's a lot of work. but I don't know. It is hard, but I found rubrics, to be somewhat helpful. At least then they understand what the minimum requirements are and
Yes.
The different categories that would be emphasized. But
yeah, the frequent problem with rubrics is that you get exactly what's on there and nothing more. So
yeah.
So yeah, it's tough for young people these days. They have so much going on. There's so much information coming at them, distractions. But like I said, I mean, that's kind of my emphasis is growth mindset, lifelong learning. That's what we're hearing from people out there now. People who've been working for 15 years. They need to get caught up on AI. Because 15 years ago when they graduated, there was none of this stuff was out there. So they also need to keep learning.
Yep. I just had that conversation this week. It might even have been today at work. About how, how we need to just keep learning. The information is coming so fast.
Right.
And the world continues to evolve quickly. Because, I've got my doctorate, but I'm thinking, now about going back to school again this year, at least for a year, and taking some more classes just to have some structured learning and exposure from people outside of maybe my domain. So we, because that's where innovation comes, is to those broaden horizons. But yeah, it's a lot to keep up with, and I think that's really important as a community because each of us have different perspectives, and we can bring those perspectives together. And I think that helps us all learn a little faster.
Mm-hmm. Yeah, great sentiments. Thank you.
All right, look, I want to be respectful of people's time. It's been a long day. For those of us on the East Coast, I can't speak to the West Coasters. But look, I first of all, thanks for everyone for helping Mark out. I know I didn't really explain how I know Mark, and it's through my company that's based in California. We have a tight tie with UCI, and the thing I will say is that Mark is really a pioneer and a trailblazer at UCI. I think you got the gist of that when he talked about the way he saw a problem with the curriculum and worked to fix it pretty much on his own. And I think he's getting some really good results. He's not happy with himself, but I've always told him, Mark, you're doing spectacular from where you started. So and I think you guys have seen that, and I think the advice you gave him will take him to that next level too. And I think also give him some confidence to know he's not that far off. He's probably on the track more than he's off. That's probably the takeaway you should have, Mark. You can trust your gut and your judgment at this point. I think you're going in the right direction. So with that,
thank you.
I'm going to say thanks, everybody, and we'll see you hopefully at the gala. Okay, and Mark, I'll be in touch.